Hello students, I am going to present in two parts my talk on the pigeonhole principle. The pigeonhole principle is not a part of your standard class 11 and 12 curriculum. However, we felt that an exposition to the pigeonhole principle will help in the general context of problem solving. There are many examples and applications of the pigeonhole principle which one tends to ignore as being trivial. Indeed, the principle is very easily stated. Perhaps one can give two very simple examples before I actually state the principle. Let's say I take any three persons. Then it's almost common sense that two of them will be of the same gender. This is because if you take one male and one female, the third must be either a male or a female. Likewise, if I take any 13 persons, two of them must be born in the same month. The reason for this is there are 12 months in the year, and in the worst case scenario, the first 12 people are born in different months. Were that not the case, then we already have the situation where two people are born in the same month. So if we take the worst case scenario and have the first 12 people born in different months, the 13th must now be born in a month which is in common with one of the first 12. This is really the pigeonhole principle. The pigeonhole principle more specifically deals with pigeonholes and letters. Pigeonhole in olden parlance is synonymous with letter boxes. Pigeons were birds that carried letters, hence pigeonhole. What does the pigeonhole principle say? Let's say I have m pigeonholes, m letter boxes, and I have n letters. And let's say I have more letters than letter boxes. N is greater than m. So I have m letter boxes and I have n letters. And I'm going to assume that n is bigger than m. N could be as small as m plus 1. The pigeonhole principle, in the simplest version, sometimes I will call it PHP for pigeonhole principle, states that at least one letterbox, I'm kind of doing away with using pigeonhole and substituting that with a letterbox. At least one letterbox must contain at least two letters. It must contain more than one letter. There's a more generalized version of it, really an extension of this. This is a generalized version of the pigeonhole principle, which I'm writing in the same sheet. Let's say the number of letters n is k times m plus 1. Or more generally, n exceeds k times m. And there's still m letter boxes. The pigeonhole principle will then say there exists a letterbox containing more than k letters. The case where k is equal to 1 is what I call the pigeonhole principle, the basic version of it. If you put k equal to 1, then the case that I'm dealing with reduces to n greater than m, and then the conclusion is there's one letterbox that contains more than one letter. More than one letter simply means that there's at least two letters. This is a deceptively simple principle to state and an easy principle to prove or verify, but surprisingly it leads to very difficult problems. The main difficulty in solving problems with the pigeonhole principle, perhaps, is to identify the fact that the problem requires a solution by the pigeonhole principle. Once you've identified that the problem is to be solved by the pigeonhole principle, half the battle is won. The other half, which is not insignificant, is to put the formulation of the problem in terms of letters and letterboxes, to decide what should be the objects, the letters, and what are the letterboxes to put these objects into. A good pigeonhole problem is one where you can guess what these letters and letterboxes should be by virtue of the numbers, the numerals n and m given to you. For example, a typical pigeonhole problem, which is a good problem, should be something to the effect where the number of letters is exactly one more than the number of letterboxes, or more generally, exactly one more than some multiple of the number of letterboxes. Because from there, you can kind of guess how many letterboxes to choose and how many letters to put in each of those boxes by applying the pigeonhole principle. What I'm going to do from now on is give you a bunch of problems to look at. We're going to try and analyze to the extent that we can and how we could work on those problems, how we could come up with the pigeonholes, the letterboxes, and the letters, and then write the solution. Let me begin with a relatively straightforward application of the pigeonhole principle. My first problem, this is on your monitor, but I will read this out anyways. There are 5 lattice points in the plane. For those who are not familiar with what a lattice point is, it's simply a point, both of whose coordinates are integers. They need not be positive integers. They could be 0. So plainly, a lattice point is a point x comma y, where x and y are both integers. So now we're picking 5 lattice points at random in the plane. The problem is to prove that you can always choose 2 of these points from amongst these 5, such that the line segment joining these 2 points that you chose passes through another lattice point. So what does this problem say? This problem says that you pick any 5 lattice points you wish, place them on the plane, and prove that there must exist 2 of these 5 so that the line segment joining these 2 passes through a lattice point. Obviously, you're not allowed to choose the end points as one of those lattice points. So when I say passes through, I mean passes through as an internal point. Why did I pick this problem right at the beginning? Well, one of the reasons I picked this right at the beginning was because this is geometric, a little bit visual, a little bit easier to see. I have with me a little grid. I'm not sure if you can see it. I'm going to seemingly at random pick 5 points. I'm not sure if they're really at random, but I'm going to pick 5 points here. So I have labeled them P1, P2, P3, P4, and P5 in random order. These are all lattice points. That means each of these points have coordinates, both of which are integers. I'm not sure if you can see this. Maybe you can zoom in. But I have the sheet of paper which is perfectly designed for a problem like this, because I already have grids placed in there. All right, so one thing is clear, that the letters that go into the letterboxes are precisely these points. There are 5 given to me, and these must be the 5 letters that I have to put into my letterboxes. So the question is, how do I construct the letterboxes? How do I think of them? And so on and so forth. Well, if it's to be a good pigeonhole principle problem, I should somehow think of 4 letterboxes, 4 being 1 less than 5. Because then the net result of the pigeonhole principle will simply be that 2 of these letters, 2 of these points in this case, will go into the same letterbox. Now, going into the same letterbox must somehow signify the fact that the line joining these points, not sure where the line comes in though, where the line joining these points must pass through a lattice point. Now, this is what makes this a little tricky, but I still chose this first because, like all good pigeonhole principle problems, you have the feeling of, oh, this is fairly straightforward if I've seen the solution before. So the hard part, of course, is not to understand the solution, but rather to have figured out how you could have got there. All right. So now I have to somehow correlate the number 4 with the fact that if 2 of these points, lattice points, go into these 4 classes, these 4 letter boxes, they will have the property that the line segment joining them is necessarily a lattice point. A little bit of basic coordinate geometry would be handy. Let's say I have 2 points, x and y, or a and b, a comma b I should say, joined to c comma d. There is a very simple formula for the midpoint of this. The midpoint of 2 points with coordinates a comma b and c comma d is given by a plus c over 2, b plus d over 2. I have to be a little careful because I'm kind of going on the margin, close to the margin. I hope you can see that. So that's the midpoint formula for in coordinate geometry for 2 points out there. So what we're going to do out here is basically focus on a property that requires the midpoint to be a lattice point. And that has to do with parity. The moment you divide by 2 and you insist on thinking of lattice points, it immediately leads you to think, what is the parity of these numbers a, b, c, d? So what is the parity of an integer? The parity of an integer is simply whether it is odd or even. An even integer has an even parity, if you like. It's a number that is divisible by 2. Those that are not are called odd integers, and you could say they have odd parity. So plainly put, all integers are in 2 classes, either the odd parity class or the even parity class. Now, the basic point out here is simply the observation that if a and c are both odd, or if a and c are both even, then a plus c by 2 would necessarily be an integer. That is because odd plus odd is even, and even plus even is also even. On the other hand, if a and c happen to be opposite parity, one odd and the other even, then a plus c by 2 is not an integer. This is the conclusion you do not desire when you want that midpoint to be a lattice point. So working backwards, I am trying to figure out if it is possible to get a pair of lattice points, a comma b and c comma d, so that both a and c have the same parity. So let me just write it out here. A and c have the same parity, and at the same time b and d have the same parity. This has to be simultaneously the case. I hope you understood why I'm focusing on that. If a and c have the same parity, it is true that a plus c by 2 is an integer, and likewise b plus d by 2 is an integer if b and d have the same parity. Now, this is basically the method I'm going to apply to solve this problem, to put my letters in my letter boxes. My letters are my 5 points. What are my letter boxes? So for my letter boxes, and I'm going to put a little box out here with 4 divisions. I'd better have exactly 4 letter boxes. And I'm going to put some symbols for myself that will tell me what I'm thinking in terms of this letter boxes. The 4 letter boxes are going to be labeled in order, O and O for odd and odd, O and E for odd and even, E and O for, I think I've missed writing this. This should be even and odd, E and O, and the last one is E and E for even and even. So remember, I am putting an order in this labeling. So for example, the second and the third boxes are different. O and E is different from E and O. So the point P1 goes into the box O comma O if both its coordinates are odd integers. It goes into the box O and E if the first coordinate is odd and the second is even, and so on and so forth. Now, it's clear that each of these 5 points will go into one and only one box according to the parity of each of its coordinates. And as I said before, the pigeonhole principle takes over. 2 of these points will go into the same box. Once they get into the same box, for example, they get into box number 2, the first coordinate is odd in both cases. The second coordinate is even in both cases. And therefore, the midpoint is necessarily an integer point, is necessarily a lattice point. So this completes, by pigeonhole principle, the proof that any 5 points that are lattice points placed in the plane must contain 2 such that the line segment joining them must contain a lattice point. In fact, as a midpoint, for example. Let me go on into something slightly different, which is a slightly less geometrical flavor, but equally straightforward. So imagine that you're in a party, and there are n people who are in this party. There are n persons in this room, and n, of course, is greater than 1. I say, of course, because, well, from what I'm going to say after this, it will become apparent that n equal to 1 will prove nothing. What am I trying to prove? What I'm trying to prove is that there will be in this group 2 persons amongst these n that know an equal number of persons. So your world right now is the party. You're only focusing on the n persons in the room. Let's say n is equal to 10, for instance. And you're asking the question, why is it the case, or you're asking to prove the question that there must be 2 in this room who know an equal number of persons. Now, we're not going to define what one means by number or acquaintances. You can use any definition you wish, so long as it's consistent. We will simply assume, of course, that if A knows B, that B knows A. And we're not worried about whether A knows himself or herself. So with these parameters, we need to prove that there must be 2 in the room who know the same number of persons within that room. All right. This is a fairly straightforward application of the pigeonhole principle. Let me take a fresh sheet. And let me just call these persons P1, P2, P3, all the way till Pn. Now, since when I count in terms of the number of acquaintances or in terms of number of how many people I know, I don't count myself in that list. The most that you can know within that room is n minus 1. It's 1 less than the number of persons in the room. So if I call that number something like n1 for the number of persons known by person 1, then that number is no more than n minus 1. 1 less than the number of persons in the room. For the lower end, I can end up knowing nobody, which is very unlikely if I'm called to a party, because I probably know the host. But whatever. As a mathematical problem, it's possible that the number of persons known by a specific person is as small as 0. It can't get lower than that. So if you look at this list, each of these numbers, n1, n2, n3, and so on and so forth, will be between 0 and n minus 1. Now, the main thing out here is to figure out what the letter boxes are. It's quite clear what the letters are. The letters are simply the persons in some guise that go into the letter boxes. So what do I want to do for the letters? Well, what do I want to prove in the end? What I want to prove in the end is that there are 2 persons who know the same number of, who have the same number of acquaintances. So clearly, what I want to end up with is a situation where 2 letters go into the same letter box, provided they know the same number of acquaintances. They have the same number of acquaintances. So in some sense, a box is to be filled in accordance with the number of people they know. So that gives me a hint. I now draw my boxes, and I label them 0 through n minus 1. There are n boxes, because the smallest is 0 and the largest is n minus 1. And what I'm going to essentially try and do is put a person in a box according as the number of persons he or she knows. So example, if P1 knows 5 persons, then I will put P1 in box number 5. Well, it's almost done and dusted because it's quite clear how I want to do this. I want to put the persons in the letter boxes. The letter boxes almost define themselves because of the end result that I want two persons to be in the same letter box if and only if they have the same number of acquaintances. But there's a catch. The catch in doing this is that the number of persons is n and the number of letterboxes is also n. That's not what I was looking for when I tried to do the pigeonhole principle. When I tried to do the pigeonhole principle, I wanted my number of letters to exceed my number of letterboxes by 1. Without that, I have a little bit of a problem. I can't quite apply the pigeonhole principle directly. So let's see how we can amend that situation, in this particular problem. Well, it so happens that you can't have the situation of 0 and n minus 1 going together. I'm going to write 0 and 1 can't be together. This is all I'm going to write, and I'm going to explain what I mean by that. What I mean is that if you look at the collection of numbers, n1 and so on, which denotes the number of people that each of these persons know, it's not possible that one of these ni's is 0 and the other ni, or another ni is n minus 1. Think about that. What do you mean when you say that the number of persons known by a specific person, P1, is 0? It means P1 knows absolutely nobody in that list. But well, if P1 knows nobody in that list, there's at least one person that everybody doesn't know. Therefore, it's not possible for anybody else in that list to simultaneously have n minus 1 friends. Because for one, P1 is not a friend, not an acquaintance, and therefore, at the worst, the maximum number of friends any such person can have is n minus 2, if you assume that P1 or somebody else has no friends. By exactly the same logic, if somebody knows n minus 1 persons, then he or she knows everybody else. And if they know everybody else, then everybody knows at least one person. So what you have deduced, and this is very significant for this problem, is you either fill up box 0 or you fill up box n minus 1, and you can't fill up both. It is possible that you fill up none. What do I mean by filling up a box? Well, let me remind myself. I put P1 in a box that denotes the number of persons he or she knows. And since 0 and n minus 1 can't go together, effectively I have either the situation where this box doesn't exist, and n minus 1 box may and may not, or, and I'll draw this picture one more time and label it kind of the same way all the way till here, and I'm not filling up this box. And I may and may not fill up box 0. So in any case, you will not have more than n minus 1 letter boxes to fill. And you still have the n letters. Not classic pigeonhole, because one cannot say for sure that all these boxes will be filled or empty. It doesn't matter. The point is that the number of letters or the number of persons exceeds the number of letter boxes. That's all I really needed. I needed n to be more than the number of letter boxes. The moment I have that, I'm off and running. I have the pigeonhole principle, and you've heard the last bit of it, because the argument essentially is working backwards. It's basically trying to figure out how you might choose your letter boxes so that things work out. Since we've already worked that out, we know that this is going to suffice as a solution. In other words, by pigeonhole principle, I have two persons, let's say P1 and P2, that go into the same box. Well, that simply means that they know the same number of persons. And that's the end of this problem. A slightly different flavor to the third problem. It actually comes in several parts. And not only does it come in several parts, I'm going to also add a little bit to the significance of the numbers out there. I've kind of made it a little general. I could have probably started with a specific value of n, like 10 or 100 or whatever. But I feel that this is equally easily understood without necessarily resorting to a specific value of n. If in the course of my explanation of this problem, you feel that you are struggling, or for other reasons, you could choose n to be a sufficiently small positive number and work this problem through. And once you've understood what I've said for a general n in your specific instance, you could probably rewind this tape and see how this generalizes to the situation that I've talked about. All these three problems are connected. So although the first two are relatively straightforward and the third is not, I chose to put them together. Really speaking, the third part of this problem is significantly harder, meaning the choice of the letters and the letter boxes significantly harder to make than in the first two cases. But because the base is the same, I decided to put them together. Let me just read the problem out. So you have the set of positive integers, the first 2n of them. It's important that you take the first 2n of them, the first even number of integers, for example, the first 200 or the first 20. And then from this collection of the first 2n integers, you pick any n plus 1 of them. Any n plus 1. It's a three-parter. Each of them has to be proven. The first conclusion that you are required to draw is that you must have chosen 2 from amongst this n plus 1 that are consecutive. That means they differ by 1. The second conclusion is that you must have chosen 2 that are co-prime. That means the GCD is 1. Well, let me stop right there. And if you've thought about this, you will realize that the two are related. One is connected to the other. Let's say, for instance, I have managed to prove the statement 1, that I've managed to prove that I can find 2 that are consecutive. Now, you know that if you have 2 consecutive integers, the GCD must be 1. That's because if you have a number d that divides a and also divides a plus 1, then it divides the difference, and the difference is 1. And therefore, any common divisor of 2 consecutive integers has to be 1. Therefore, if you somehow have succeeded in proving statement 1, that there must be 2 that are consecutive, you have also succeeded in proving that they are co-prime. On the other hand, if you've succeeded in proving that you have 2 co-prime integers, it is not necessarily the case that they must be consecutive. So making one statement is stronger than the other, and it's tempting to make the stronger statement if possible. The third one is unrelated and in some sense very different from the conclusion of the second. The second one says there will be 2 that have nothing in common. The third says there will be 2 so that one divides the other. So this is the problem which I have to prove. Let me take a fresh sheet of paper, write the basics down of what I'm required to prove. So my set that I had was 1 through to n. And what I'm required to pick from here is choose any n plus 1 from the set. And I'm required to prove 3 things. The first thing that I was required to prove is that 2 are consecutive. Bear in mind that if I prove this, I've also proven, and so I will write an implication out here, I've also proven that 2 are co-prime. 2 are co-prime. So proving 1 will prove 2 together, and that's the route I will take. All right, so I have to choose n plus 1 numbers from this collection. The hint here is because it's a pigeonhole principle problem, I don't have to worry on that count, on the method of attack, because this is only about pigeonhole principle problems. I have to somehow construct n letter boxes. 2 are consecutive. 2 are consecutive defines itself. That means if I have to apply the pigeonhole principle problem, I have to have exactly n pigeonholes, n letter boxes. And the conclusion will be that 2 of these numbers go into the same letterbox and share the property that they are consecutive. Therefore, I have no option. I have to place consecutive integers in each letterbox. There's one simple way of doing it, and that is in the first letterbox you place 1 and 2. In the second, you place 3 and 4. In the third, you place 5 and 6, and so on and so forth. And in the last one, you place 2n minus 1 and 2n. This is pretty much the only way of placing consecutive integers into n letterboxes. You can't, for instance, leave 1 in the lurch in a letterbox by itself, because the only thing that 1 can pair up with is 2. And similarly, you can see that 3 must go with 4 and so on and so forth. Pretty much that's all I could have done. The rest of it is fairly straightforward. When I pick any n plus 1 numbers from 1 to 2n, it's quite clear that 2 of them will go into the same letterbox by Pigeonhole Principle. Going into the same letterbox means these 2 numbers are precisely a pair of consecutive integers. Once they're consecutive, they're also co-prime. Now comes the harder problem. For this, I'm going to turn the page and take a fresh sheet and remind myself what the S is. It's still the same set, and I still have to choose n plus 1 from S. But this time my goal is slightly different. I have to show that there exists 2 numbers, A and B, from this collection, such that A divides B. My work would be straightforward if one of these numbers was 1, because 1 divides everything. But really, I have no choice in the matter, because I can't choose 1 for sure, because I don't know which n plus 1 numbers I've chosen. So I have to be cleverer than that or more general than that. All right, Pigeonhole Principle means that I again draw my customary n boxes, and all of it lies in how I label them and what I place on those boxes. The labeling is not important. You can label anything you want for the n boxes. You can label them P1, P2 till Pn. But until you realize what you put on those boxes, it amounts to nothing, the labeling. Nevertheless, I'm going to label the boxes 1, 3, 5. Perhaps the pattern is clear. I'm going to put all the odd integers in there. I haven't placed enough space in the last box to put my label. The last label is the largest odd integer less than 2n, less than equal to 2n. It's 2n minus 1. There are exactly n even integers between 1 and 2n, exactly n odd integers between 1 and 2n. And therefore, what I've done is used up all my odd integers and put my labels for the n boxes as one of those odd integers, 1 through 2n minus 1. Now comes the clever part. How do I choose to place my numbers in these boxes? Well, you take any number from this n plus 1 numbers. It's a basic fact, which you probably know, that you can divide m into prime factors. Another way of saying this, in this particular instance, because I don't need the full statement of that result, if m is odd, leave it the way it is. If m is odd, it will be one of the numbers from within the collection 1, 3, 5 till 2n minus 1. It goes into the box labeled m. If it is not odd, then it is even. And if it is even, then you can divide m by 2 and ask the question whether or not that is odd. If it is, do the same thing that I said in step 1. And if this is even, so if this is odd, then, so I should not write it like this. If this is odd, then place this in box m by 2. And if m by 2 is even, then you keep dividing. So plainly put, I could have said this much more easily in the following fashion. Think of m as being a power of 2 multiplied by something, which I will simply call O. It's an odd symbol, but it's an OK symbol for an odd integer. E here is at least 0. E could be 0. So this is the basic fact that I'm assuming to be correct for any positive integer. Any positive integer can be written as a power of 2, including the 0th power of 2, multiplied by an odd integer. So this O here, maybe not a great choice because it looks like a 0. So let me just put a little marker there. That O is odd. So any m can be written as a power of 2 multiplied by an odd integer, and in exactly one way. I will not go into the explanation of that, but it's kind of fairly clear what the algorithm is. As I said before, if m is odd, do nothing with it. Otherwise, it is even, and you keep dividing by 2 until you hit an odd integer. So your final step will be the largest odd divisor of m. So what I'm looking at is the largest odd divisor of this m. Now, if it is the largest odd divisor of m, it is not more than m, and m is not more than 2m or 2n, and therefore O has to be a number between 1 and 2n minus 1. Now, the algorithm or the procedure or the trick for this is take each of these n plus 1 numbers, relate that number m to the largest odd divisor it has, and place it into that box labeled O. And O has to be one of those n boxes. This is the big trick out here. You might have the feeling that, well, once you see the next step, you have a minute more and you are done with the proof, and you would say this is no big deal. Well, it is. This is one of the harder pigeonhole principle problems that you can think of. The simplest way of evaluating that is ask yourself or ask a friend, would you have thought of this procedure? And that is how you evaluate a problem. You do not evaluate a problem by the length of the proof of the problem. All right. That said, the pigeonhole principle now says that there are two of these numbers, m1 and m2, or a and b, that have gone into the same box. Since I've got all my material here, let me not change pages. Let's say I have got this box labeled O, my generic symbol. And let's say I've got this number a in there as well as the number b in there. And of course, a and b are distinct numbers. They are from that set of n plus 1 numbers. Now, what is it that made a go into that box O? The reason a went into that box was because a was equal to 2 times some e times this O. And the reason b went into the box was because it is 2 times f into the sum O, the same O. And e and f here are non-negative integers. They could be 0, but they're certainly integers. Now, the moment you see the form that a takes and the form that b takes, it's quite clear that supposing a is less than, let's say e is less than f, same as saying a is less than b, it's very clear that this implies that a will divide b. Remember that a and b are distinct, they're not equal. Even if they were, there would be nothing wrong in my stating that a divides b. But implicit in the assumption when one says choose n plus 1 numbers is the fact that I've chosen n plus 1 distinct numbers. It becomes a triviality if you chose n plus 1 numbers where 2 of them were the same, because the conclusion is that one divides the other. So whichever way you take it, you may as well put in the assumption that n plus 1 are distinct, and in that case e would be less than f, or e would be greater than f, it doesn't matter. Let's say e is less than f, and you have a divides b. All right. So that's the proof of this third part. But I have a little bit to add to this particular set of problems. So it's probably a wise idea to run this sheet through one more time so that we can see what this problem stated before I say why this problem is particularly significant in some sense. So the problem asks you to choose n plus 1 numbers from the set of the first 2n numbers and draw 3 different conclusions. The way we did things, one of those conclusions followed from another. One implied 2. So we actually only proved 2 of these. Now, in most of these combinatorial problems, there is a particular reason why a certain selection is made. For example, when you're asked to choose any n plus 1 numbers from 1 to 2n and draw conclusions, some of you might start wondering, what is the significance of choosing n plus 1? Why couldn't I have chosen fewer than n plus 1 and drawn the same conclusion? It's quite clear, of course, that if you chose more than n plus 1 numbers, the same conclusion would have been valid, could have been drawn, because, for example, if you chose n plus 2 numbers, you can throw one number away for free and draw the conclusions on the n plus 1 numbers. And therefore, anything beyond n plus 1 is a given so far as the conclusions are concerned. What about choosing n numbers from 2n, the first 2n numbers? Is it correct that each of these three conclusions hold? This is what I wanted to stress on. And I want to tell you that n plus 1 is significant in the fact that if I had chosen n numbers instead of n plus 1, none of these three conclusions would have been correct. So let me just take a minute to show you this. So I have my S again, 1 through to n. And this time I choose only n from this set. And I want to show that none of those conclusions, none of the conclusions, 1, 2, 3, hold. None of them hold. So in mathematics, when you're trying to prove something, you're trying to prove it in all different cases. So if there's even one case where the conclusion is not valid, then the statement is not correct. So I'm going to count on that to give you a proof of the fact that n does not work. So far as the numbers 1 to 2n are concerned, you choose any of n of them, and you have to prove that 2 have to be consecutive. Well, you want to avoid consecutive integers. So to avoid 1, you want to avoid consecutive integers. Well, there's actually two ways of doing it, and that's fairly straightforward. Your gut feeling, you start with 1, you want to avoid the second one, so you then take 3, and you miss out every other one. You're kind of taking the set of all odd integers. In fact, you could even have begun with 2, and you still had margin for it, taken all the even integers. In each case, there would be n integers picked, and it would happen that no two of them are consecutive. What about avoiding 2? In avoiding 2, you want to avoid the fact that you must have the situation where 2 are co-prime. Well, you could pick the second collection. So you could pick the even integers. Certainly, they are all even, and therefore, this collection doesn't have 2 co-prime integers. What about avoiding 3? Avoiding 3 is also not very difficult, not very tricky to come up with. Here the conclusion was that I must pick 2 so that one would divide the other. So if you take the smallest one to be fairly large, then there is no scope for a multiple of it to be within the set. In other words, if I picked the smallest one to be n plus 1, and I went on, it's quite clear that any multiple of n plus 1, which is not n plus 1 itself, will exceed 2n. And if the smallest number in this collection is such that twice that number exceeds everything in that set, there's no scope of A dividing B from within this collection. And luckily for me, there is precisely n elements in this set. So it is possible to choose n elements from this set and avoid A dividing B. Now, let me switch to one of my favorite pigeonhole principle problems, also to do with numbers, but in a totally different sense. Supposing I give you any collection of n integers. It will again make sense if you take the integers to be distinct, but it doesn't have to be so. So in this particular instance, actually, you can take one or more of them, 2 or more of them to be the same. What does this problem ask you? It says, take any 10 integers. There will always be a non-empty subset, the sum of whose numbers is a multiple of n. For example, if you pick any 10 numbers, 10 positive integers, 10 integers can be negative as well, can be 0 as well. You have to have some subset of these 10 numbers which add up to a multiple of 10. In other words, there'll be some subset of this which, when you add up, will end in 0. Whereas this example is going to do me no good towards a general proof. Nevertheless, let me just take a so-called random collection of 10 integers. For no particular reason, I'm writing the sequence of numbers. There's actually a collection. The sequence, the ordering does not matter. So I've picked
I didn't think it would be that hard for me to reel off a bunch of numbers, but I guess it is. I've reeled off 1, 2, 3, 4, 5, 6, 7. I need 3 more numbers. I don't know how many of you see the significance of the last 3, but if you don't, that's fine. There's something common between those last 3 numbers. I hope I've listed 10. Now, what this problem says is that no matter which collection of 10 numbers you pick, they don't have to be distinct, in fact, and some of them could be negative. I could have chosen 0, but I didn't for a reason. You have to have a sub-collection of this, non-empty, so that when you add up the numbers in the sub-collection, that sum is a multiple of 10, which simply means that when you add those numbers up, it ends in a 0. Well, probably several ways of doing this. The first thing that strikes me is to pick these two. 28 and 8192, whatever it is a multiple of 10. I've succeeded in finding 2 numbers from this collection, the sum of which is a multiple of 10. Well, what you have to actually demonstrate is this is always the case, not just for 10 numbers, but in fact for any n integers, positive, negative, 0. And you can see why 0 would be a triviality. The moment you pick 0, the single element 0 would have a sum 0, and it would be a multiple of every n. All right, so what do I do out here? I again have to have my boxes. Boxes kind of explain themselves in this situation. I'm going to label them 1 through 9. Why are these 10 boxes significant, or why did I say that this is kind of the way to go? It's because my 10 boxes signify the different situations that you can have when you divide a number by 10. So I guess I'm doing this for 10, and then I'm going to generalize. It's probably the easier way to go, because it's transparent what I do from 10 to n. So let me just take the special case n is equal to 10. So now I'm taking any 10 numbers. Let's just call this a1 through a10. These are 10 integers. And to go with these 10 integers, I have 10 boxes. These boxes are labeled 0 to 9. You put an integer in a box, 0, provided when you divide by 10, it leaves the remainder 0. It goes into box 1 if when divided by 10, it leaves the remainder 1. Since there are 10 different choices for remainders, because you're dividing by 10, and these choices are 0 to 9, the letter boxes kind of pick themselves. There's almost no other choice you could have had. Why should I concern myself with remainders and the letter boxes that should necessarily relate to them? Well, because the problem asks you about divisibility. The final answer has to do with whether or not a certain subset is a multiple of. So what I really want to do is focus on box number 0 in some sense, because that is what somehow signifies whether or not something is a multiple of 0. And therefore, it's kind of natural to put my letter boxes to be in one-to-one correspondence, labeled according as the remainder when divided by 10. All right, that's fairly straightforward. Now comes the real clever part. And this is what makes this problem significantly harder than a standard pigeonhole principle problem. I'm going to construct a bunch of sums that have to do with, that are related to this sequence of numbers. So what I will do now is kind of write the 10 numbers in a certain random sequence. A1 is first and A2 is second. For the first sum, I will consider just the first number. For the second sum, I will take the first 2, and therefore it matters with what your sequence is. For S3, I will take the first 3 in the sequence, A1, A2, and A3, and so on and so forth. And my last sum, S10, will be actually the sum of all these numbers. And here is the clever part. The clever part is in actually deciding that I don't really want to put these 10 numbers into these 10 boxes. Why wouldn't I want to do it? For starters, that's not going to help you. Secondly, this is not at all what I wanted. What I wanted was the fact that there would be a subset of this collection whose sum would be 0. If I was able to draw this conclusion by simply putting the singletons in these boxes, then I'm kind of hoping that singleton elements, individual elements, would be multiples of 10, which is far from the case. It's very straightforward to pick 10 numbers, none of which is a multiple of 10. That cannot be the conclusion, therefore. Therefore, I should certainly not think in terms of putting just the numbers into those boxes. That could not have been the reason. That still doesn't justify why I would think of putting the sequence in order. Well, this is one of the clever parts of Pigeonhole Principle. Some of these defy logic in some sense. There's no straightforward reasoning as to why one would have thought of this. So you construct the sequence of 10 numbers from the original sequence at random, S1 to S10, and now you do what I wanted to do. That is, you place these numbers into the boxes according as their remainder when divided by 10. And because the remainder is unique when you divide by 10, S1 to S10 will occupy exactly one letterbox each from amongst 0 to 9. Is this exactly pigeonhole? Not really, because now my number of letters equals the number of letterboxes. They're both equal to 10. Pigeonhole will come in a minute. Supposing one of these numbers, S1 to S10, goes into box 0. Let's say for definiteness, S5 goes into box 0. If S5 goes into box 0, so if S5 goes into box 0, then by definition, 10 will divide S5. And S5 is simply the sum of the first 5 terms in the sequence of numbers that I took. And therefore, I have a subset consisting of A1 till A5, whose sum is a multiple of 10, which is what I sought to do in this particular problem. So I'm done if any one of these numbers, S1 to S10, fills up box 0. This is not pigeonhole, but now I'm into pigeonhole. If this is not the case, that is, if S5 does not go into 0, in fact, none of the SIs go into 0, then I really have 9 choices to put these 10 numbers into. And now I'm into pigeonhole. I conclude that 2 of these numbers, some Si and Sj, let's say for definiteness S3 and S7, go into the same box. And let's say that box is number 5. You can generalize this and write your own symbols for it. Now, when you say that S3 and S7 go into box 5, it means that they both leave a remainder of 5 when divided by 10. It simply means that the last digit is equal to 5, whether it comes with a plus sign or a minus sign. It also means that if you take the difference will be a multiple of 10. It must end in 0. So it means that 10 must divide the difference between S7 and S3. In fact, as long as S3 and S7 went into the same box, it didn't have to be box 5, the difference would be a multiple of 10. It's a very straightforward property of divisibility. You can write this up yourself and figure out why this would be the case. That if S3 and S7, or more generally Si and Sj, go into the same box, let's say box R, then Si and Sj can both be written in the form some multiple of 10 plus R. And when you take the difference between Si and Sj in the right order, then you get a multiple of 10. Now, what is S3 minus S7? S3 minus S7 is actually, by definition, A4, and I don't have space here, so I'm going to put a little dot, till A7. Because S7 is the first 7 numbers, S3 is the first 3 numbers, the difference would be the last 4. And you've proven that 10 divides this. It divides that collection of 4 numbers. All this can be generalized, but I thought it would make sense after doing all these general cases to work with a specific instance of n. It's fairly transparent to transfer this proof, to extend this proof, to write this proof up, in fact, for any n. So as an exercise, I urge you to actually work this out, replacing 10 by n, any n, in a proof. So I will stop here because we're kind of running out of time for the day.
And I will come back with more examples, more varied examples, maybe some more difficult ones in my second lecture. I look forward to seeing you whenever the next lecture is. Thank you.